Good afternoon and welcome to this lecture session in the EduSat course. Today's discussion will focus on spectral signatures and image interpretation. As you know, a picture always describes more and conveys more, which we have already seen in the remote sensing images. By now you must all be familiar with this workflow of the physical basis of remote sensing. What we require is a source of energy, which in most cases is the sun when we talk about passive remote sensing. The electromagnetic radiations from the sun travel through the atmosphere, all the while interacting with the constituents of the atmosphere, and then they reach the surface of the earth and interact with all the objects or targets that are there on the surface of the earth. After this interaction, the EMR travels back and is measured. All the EMR that travels towards the sensor is measured on the devices on the sensor, and then it is transmitted, processed and given to users for various kinds of applications. The product that we receive is in the form of an image or a photograph. You must also by now have understood the importance of the electromagnetic spectrum and the electromagnetic radiation, because it is this spectrum and the behavior of objects based on this, how they interact with the various regions of the spectrum, is what we see on the image, and then we try and interpret those manifestations on the image. So as you see, the electromagnetic spectrum ranges from shorter wavelengths to the longer wavelengths, starting from the gamma rays and the X-rays and to including the microwaves and the longer wavelengths, which are microwaves and broadcast radio waves, which we call the communication waves. There are several regions of the spectrum which must already have been discussed, and these are useful for remote sensing. Basically we are concerned with the visible portion, the infrared and the microwave region of the spectrum for interpreting images for natural resources management and monitoring. Now how would you describe or define image interpretation? We could have several definitions, the easiest being that analysis of remote sensing imagery involves the identification of various targets in the image. So we basically need to identify the objects that we see in the image and then interpret and come to a conclusion as to why the objects appear on the image as they do. Targets or objects may be defined in terms of the way in which they reflect or emit radiation. Meaning that if an object appears bright on the image, there is a certain amount of energy that must have been reflected, most probably a larger amount of energy, and if it appears dark or grey, then we would have lesser amount of energy being reflected or emitted from that region on the surface of the earth. Now radiation is measured and recorded by the sensor as described in the previous diagram, and ultimately this is depicted as an image product, which could be either an aerial photograph or a satellite image. So the act of examining images to identify objects and to judge their significance on the images using images is known as image interpretation. We could also say that it is the information extraction process from the images. Once we have the image products after pre-processing, etc., we could use those images for certain decision making problems that require decision making, and this involves a considerable amount of subjective judgment. They are not objective as in mathematical problems, but interpreters could, depending on their knowledge and their previous background, could make subjective judgments on various images. An interpreter, on the other hand, is a specialist who is trained in the study of photography or imagery, and in addition to this, he or she could also be an expert in his own discipline. So a geologist who uses images to make interpretations, or maybe a forester expert in forestry or an expert in urban management, etc., urban studies, could use images to make certain decisions. Now how do you define images? Images are basically a pictorial representation of an object or a scene. Images could be either analog, that is hard copy images, or digital. you have yet not been exposed to the structure of digital images, etc. You will be dealing with them in a short while when you begin digital image processing. But just to summarize, a digital image is made up of squares or rectangular areas which we call pixels, and each pixel is associated with a pixel value or a digital or a numerical value, and this value depends on the amount of reflected energy from the ground. So as I said, if this value is higher, it means that it has reflected more and would be a brighter object on the image, and vice versa. So this picture depicts the structure of a digital image. Since we have multi-spectral images, of several of which you are probably aware of, names of several sensors you must be aware of the names of several sensors by now. So it's an array of numbers, each layer corresponding to one region of the electromagnetic spectrum, and these numbers, as I said, are digital numbers or spectral values or brightness values. So even though this region and this region are same geographically, they would have varying digital numbers, because we are now, when we are imaging these bands or channels, we are changing the region of the electromagnetic spectrum through which these are seen. Now since we have multispectral scanners or multispectral images that are available, we are also able to see in multiple regions of the spectrum, that is not just in the visible region in which human eyes are sensitive to seeing, but we can see the infrared region, we can also see in the microwave region, and so on. Now this enables us to see things not only, or see a color composite on screen, not only of the true colors that are depicted, that we may depict or see as seen on the terrain, but we can create based on the different bands that we have in the image or the different channels that we have in the image, we can see in a false color composite. The advantage of viewing in a false color composite is that we are able to see objects which reflect differently, or which give you a characteristic reflectance in a particular band. We are able to choose that band and have a best band combination, which gives me or shows me or displays the object of interest in the best possible manner for better interpretation. Now the question arises as to what makes interpretation of imagery more difficult than the everyday visual interpretation of our surroundings. We are used to seeing images, then why do we need this special kind of training to be able to access information from these remotely sensed images? The most important point is that we lose our sense of depth when viewing a two-dimensional image. In everyday life, we are used to seeing in 3 dimensions, whereas when I look at a monoscopic image or a single image, I lose my sense of depth, and unless we are able to view it stereoscopically, so as to simulate the 3rd dimension of height, we are losing the sense of depth and we see everything as a flat entity. That sometimes hampers interpretation. Viewing objects from directly above also provides a perspective which is different from the one that we are used to. That is, in everyday life we are used to seeing in a horizontal perspective, whereas aerial images or space-based images give us a vertical perspective, and here we are only able to see the objects as they are visible from on top. So I only get a top view of the object, so I need to imagine as to how, I don't see the facade or I don't see the profile of the objects. Now combining an unfamiliar perspective with a very different scale and a lack of recognizable detail can also make familiar objects unrecognizable in the image. That is why one needs to be familiar with how they would look like when I see them from an unfamiliar perspective, that is a vertical perspective. And finally, we are used to seeing only the visible wavelengths. As I mentioned, sensors are capable of imaging in wavelengths other than the visible wavelengths. So you have data in microwaves, in the microwave wavelengths, we have data in the infrared wavelengths and other wavelengths other than the visible portion. And the imaging of wavelengths outside this window is more difficult for us to comprehend. That is why we need to be made familiar with the properties of the electromagnetic spectrum and how it would interact with various targets on the surface of the earth. Another important thing that the user has to be very familiar with is the characteristics of the image, which are defined basically by the resolutions or specifications which define the data type, so that the user is aware of which kind of data would be the best suited for the kind of application that he or she wishes to use it for. So spectral resolution, which is the part of the electromagnetic spectrum that is measured, that is the narrowness of the band that you are viewing in. This is important where you have similarly reflecting objects, say minerals or species of trees and so on. So if you wish to distinguish between two species of trees, you would probably need a very fine spectral resolution. A radiometric resolution is the smallest difference in energy that can be measured. So this is the sharpness, it defines the sharpness of the image. Spatial resolution is the detail manifests itself in the details that we see. So the smallest unit area measured. So if I have a spatial resolution of or a pixel size of say 1 meter and I have a pixel size of 5 meters or 10 meters, the kind of details that I will see on both these data sets will be different. The 10 meter data set will show me coarser details and the 1 meter spatial resolution data set will show me more finer details. Temporal resolution or revisit time is of course the time between two successive image acquisitions over the same area. These kind of temporally varying images help users in doing change detection studies. So if an activity or if a phenomena has happened at a particular time, I could assess, the user could assess what exactly has happened on the ground by viewing the image, and if I have a post scenario image and a pre-scenario image, I could make a comparison and see maybe is there urban sprawl happening or is there encroachment happening or is forest area reducing or increasing, what is happening to agricultural area and so on and so forth. So change detection studies could be done when I use temporally varying data. Now what is the advantage of using these kind of remotely sensed images over using ground observations? First and foremost, we get a synoptic view of the area, so I am able to see in context, one object in context with the other. Images enable me to have a time freezing ability, so I see exactly what has happened at that moment in time on the ground, and therefore it is a permanent record. I can go over it over and over again at various time periods. Variable spectral resolutions let me do better analysis, and spatial resolution lets the user see objects in varying amounts of detail. Then in the long run it comes out to be more cost and time effective because I am able to see with the help of the synoptic view, I am able to see a larger area in the comfort of my laboratory, and I am also able to see things in context in relation to each other. Certain sensors also give me a stereoscopic view, that is we are as users are able to view that area in 3 dimensions, and because of this synoptic view and time freezing ability, I as a user I am able to bring out the relationship between objects. I am able to see them in context or their relationships with each other. Now how does one do interpretation, or how do I assign or label objects or groups of pixels and say that this group of pixels corresponds to maybe a water body, or this group of pixels corresponds to a vegetation area? This happens when I am able to identify spectral signatures on the image, that is I identify, or I have a unique identifier. So as you know, identity is whatever makes an entity recognizable. So if you go to a bank, you identify yourself with the help of your signatures or maybe a biometric signature, right? So a signature is something which gives an object or a piece of information its identity. Now in images, what is unique is their spectral property. So when I look at images or groups of pixels, I try and identify or identify a unique feature in terms of their spectral signatures. Spectral signatures could be defined as characteristic features which form the key to enable an object to be identified. Now these could be either spectral, spatial, temporal and polarization variations which facilitate discrimination of features on the remotely sensed data. So based on spectral, spatial, temporal and polarization variations, one can define signatures on the image which are unique to that feature. Now to do this, one plots something which we call a spectral reflectance curve. A spectral reflectance curve is a graph of the spectral reflectance of the object as a function of its wavelength. So here if you see in the figure, wavelengths are plotted on one axis and the percentage of reflectance in that wavelength is plotted on the other axis, right. So the spectral reflectance curve is a graph, as I said, of spectral reflectance of the object as a function of the wavelength, and this is useful for choosing the wavelength regions for remotely sensed data acquisition for a particular application. Now if you see, there are say water, and the physical condition of the water is mentioned as clear. So it is to be clear water, not polluted or water with many sediments. So here if you see, the graph shows you that there is very little reflectance in the visible portion, and as it reaches the near infrared, it is almost, and it dips down to 0. So that means that when you see water as a feature in the infrared region, you will see a dark signature, right, and maybe shades of grey in these regions in between in the visible portion. Similarly, if you look at the vegetation which is green physically, so healthy green vegetation, again we see a sharp rise, then a plateau, and then there are some dips, right. So these are all spectral signatures, and if I am able to identify these features or these spectral values by looking at the pixel values in the image, and I compare them to this standard spectral reflectance curve, I am as a user I am able to identify and fix an identity to those groups of pixels as to being say water or healthy green vegetation and so on. Similarly, we have the spectral reflectance curve of dry bare soil, right. So we basically plot wavelength versus percentage reflectance, and what we get is a spectral reflectance curve. Now what the significance of using spectral signatures is that spectral responses that are measured by remote sensing sensors over various features are analyzed. We get spectral reflectance and spectral emittance curves which we can analyze. The variability of spectral signatures is useful for the evaluation of conditions, maybe not for spectral identification of earth features. We can also see temporal and spatial effects on the spectral response patterns, and change detection depends on these temporal effects. Now we will look at spectral signatures of a few land cover classes one by one, beginning with vegetation. So a general characteristic of vegetation is its green color, and this color is caused by the presence of the pigment chlorophyll in the plant cell. Chlorophyll, as you know, reflects green energy more than red and blue energy, and this gives the plant its characteristic green color. So if you look at this spectral reflectance curve of healthy green vegetation, so you see that because of the leaf pigment, we have a high spectral reflectance in the near infrared region. These are two water absorption dips because of the absorption of free water in the plant tissue. This happens in the middle infrared region, right. So these are basically spectral reflectance properties that we will look at and identify in the curve, and if I see a similar curve from the image data, I am sure that I am looking at healthy green vegetation. So this is a false color composite in which a standard false color composite in which all that I see in the color red is vegetation. The first image is a spot image and the second one is an iconos image. You can also see and spot the differences between spatial resolution. This is much higher or finer spatial resolution, and this is a medium spatial resolution image. So the details that you see on both is also different. Now The major difference in leaf reflectance between species, if I talk about different species of trees, are dependent upon several physical conditions of the vegetation that we are talking about. Please note that when we are talking about spectral reflectance or the manifestation of the features on the image, it is the interaction of the electromagnetic radiation with the target on the ground, and secondly the physical condition of the object. So if it is healthy green vegetation, we will see a particular kind of reflectance pattern. If the health of the vegetation is altered or moderated, then we will see a different kind of manifestation or features on the image. Or if the plant is naturally not green, it does not contain chlorophyll naturally and contains some other pigment, then also we will be able to see that in the spectral reflectance pattern. Now, so as I said, dependent on leaf thickness, it also affects both pigment content and physiological structure. So if you have a thick leaf and if you have a thin leaf, you will see different spectral response patterns. So leaf reflectance is reduced as a result of absorption in the three major water absorption bands at 1.4 micrometers, 1.9 micrometers and 2.7 micrometers, and there are also two minor water absorption bands. So you will see dips in the spectral reflectance curve at these locations. These are also very features which are identifiable, fix an identity. Now, needle-like leaf, trees which have needle-like leaf canopies reflect significantly less in the near infrared as compared to broad-leaf vegetation. So your coniferous trees will reflect differently and deciduous type of trees, leaves will reflect differently. So the structure of the leaf, then the stage of growth, if it is an immature plant or a young plant, or if it has reached maturity, then also you will see a difference in the spectral reflectance pattern. So immature leaves, because they contain less chlorophyll and fewer air voids than older leaves, reflect more visible light than less infrared radiation. So the spectral response will be different for each. Reflectance is also affected by the health of the plant. So you see here, healthy green plants will reflect more in the infrared, which is characteristic, and the portions of the vegetation which, because of diseased or infected plants, have reduced amount of chlorophyll in the cell, will reflect differently, and this will be seen as a manifestation in the spectral response or the spectral reflectance curve. Now if you talk about the spectral signature for soil, again physical properties like moisture content, organic content, structure of the soil, iron oxide in the soil and the texture of the soil affect the amount of reflectance in various regions of the spectrum, electromagnetic spectrum. So if you talk about soil moisture, a wet soil generally appears darker because of the presence of water. Increasing soil moisture content lowers reflectance, but it does not change the shape of the curve. So if it is dry soil, it will appear bright on the image, and if it has moisture content, the object will look dark. Organic content, so if less organic content, if the soil contains less organic content, it will appear bright, and with increasing amount of decomposed organic material, it will start getting darker in color. Similarly, iron content will also affect the presence of iron, especially iron oxide. Reflectance in the green region decreases with increased iron content, but increases in the red region. So iron dominated soils, if there is more iron content in the soil, they will have strong absorption in the middle infrared region, in this region. Then soil structure will also affect the spectral reflectance. Clay soils tend to have a stronger structure, which leads to a rough surface, and they tend to retain moisture, so they have a high moisture content, and as a result low diffuse reflectance. Sandy soils on the other hand have low moisture content, and therefore as a result have a fairly high and often specular reflectance properties. Now, the next feature that we discuss is water. So, again, reflection of light in different wavelengths, the depth of water, shallow water or deep water. So, if it is shallow water, then the sediments also affect the reflectance, whereas as you go deeper into the water body and the water body gets deeper, the reflectance is only due to water content, and because in the infrared region, if we have the infrared region, it absorbs all the energy, so we see a darker water body. Suspended material will affect your spectral signature or amount of reflectance, chlorophyll content and surface roughness. Surface roughness is of specific importance when we consider images taken in the microwave region of the spectrum. Right. So, the majority of radiant flux incident upon water is either not reflected but is absorbed or transmitted, and in visible wavelengths of the electromagnetic radiation, little light is absorbed, a small amount, usually below 5%, as we saw in the curve. So, if you see here, below 5% is reflected and the rest is transmitted. Water absorbs near infrared and middle infrared strongly. There is a strong absorption in these regions. The result is sharp contrast between any water and land boundaries. So, we get a sharp contrast between land water boundaries, as you can see. We can also see suspended material. As we go deeper into the sea, we see darker, a darker object. That means it is absorbing more energy and so on. Then if we talk about spectral reflectance properties of snow, then these are affected by the grain size, that is age of the snow. So, reflectance falls at all wavelengths as grain size increases. Then the thickness of the snow. So, reflectance of snow decreases as it ages. So, if it is thicker, whether it has liquid water content in it or not. So, even slightly melting snow reduces the reflectance, because now it is melted water and water will start absorbing energy. The presence of pollutants or contaminants. So, if there are some contaminating agents like soot or other dust particles, etc., these would also reduce snow reflection in the visible region. Now, if you see here, this is a graph which shows the various features that we discussed plotted onto one graph. So, wavelengths here and the percentage reflectance here. Clear water, turbid water, that is with some sediments available in the water, wet soil, dry soil. So, dry soil would appear much brighter, healthy green vegetation. There are also two categories of vegetation plotted, that is needle-like leaves, that is coniferous trees, and broadleaf vegetation, and snow and ice. Clouds have also been plotted here. Now, if you look at the same feature plotted or displayed in different regions of the spectrum, the spectral, because of the difference in the region of the spectrum that is used to sense these images, you will see a difference in how the object appears. In certain regions there is no contrast, so the object boundaries are not well visible, that is water bodies are not well visible here. But in regions where there is good contrast between the object and the surroundings, we see clear boundaries of the feature. Okay. Similarly, we can have different kinds of displays on screen, that is a true color composite, that is actual colors as seen on the ground, or a natural color composite, and we could have a false color composite. This particular one is a standard false color composite in which vegetation appears as red and built up areas, etc., appear in the color cyan. So, you could compare and see the differences in the two. So, here you see these are all water bodies, dark features based on the spectral properties. red, the features that appear in shades of red are all vegetation, could be forest, or they could be agriculture features or grasslands and so on. The cyan tone is one corresponding to sand or built up areas. Now the other important point to remember is that similarly reflecting objects will appear as similar on the image. So you see sand and built up area because building material consists of sand and hence this reflect similarly. So you will be, even though they are physically different objects, this is river sand or dry sand and this is a built up area, they will give you the same kind of reflectance on the image because they are reflecting in the same region. Now this is a summarized table that gives you bands which are useful for particular applications. So from 0.45 to 0.52 region for water, bathymetry, etc., and some sort of vegetation. The green region is basically for the reflectance peak of vegetation, plant health and reflectance from turbid water. The red region is the chlorophyll absorption region. The near infrared region is basically again used for vegetation studies, soil moisture discrimination. The middle infrared is the best single band overall and it discriminates several features as you can see. It is also used for discriminating between snow and clouds. Then the middle infrared from 2.08 to 2.35 is useful again for discriminating several minerals, rock types and other vegetation cover and moisture. Now the methods of image interpretation could be that either you do a visual or manual image analysis or we could go for digital image processing. This is a separate section altogether and you will be discussing this in the coming lectures. What are the processes and mathematical operations involved in processing an image when you are to do digital image processing. Currently we will focus only on the visual or manual method. We could manually or visually analyze an image by doing it on a hard copy image or photograph, or I could display a digital image on screen and then do the interpretation manually. I could either do a qualitative assessment as to identifying objects based on the properties that I see on the image. Objects are bright or dark, what is the size of the objects, what is the texture of the objects and so on. Or I could do a quantitative analysis and do measurements, say what is the height, depth, area, length, etc. And then I would call it quantitative interpretation. So just to summarize the principles of image interpretation, they are based on the fact that the image is representing the pattern of the landscape in the form of a pictorial representation. These patterns would indicate the type of objects and their physical, biological and cultural relationships as seen on the ground. The most important point to keep in mind that similar objects under similar conditions reflect similarly. So if the objects are similar and they are under similar physical conditions, they might reflect similarly as we saw in the case of say shadows and water, urban areas, built up areas and sand. So on the image we will see the spectral reflectance in similar regions. Now to do this we require a systematic examination of photographs and supporting material. Interpretation is made of the physical nature of the object. So the physical condition of the object is very important. What we are interpreting is how the object is physically at that moment in time when I have the image. Now information that we are able to extract as users is proportional of course to the knowledge, skill and experience of the analyst and the methods and equipments that are used. So the factors that would govern interpretability would be training and experience of the interpreter, the nature and object of the phenomena that we are trying to assess, the quality of the input, that is the photographs. If they are of good quality, we will be able to do better interpretation. One must also use correct equipment and method of interpretation. The use of interpretational keys, guides, manuals and other aids, any ancillary information aids in interpretation and enables the interpreter to do better interpretation. For example, if you have prior knowledge of the area, we are able to assess the kind of manifestations that we see on the image in a much better way. And your methods would depend on what kind of information is to be interpreted, what is the output required. It would also depend on the accuracy of the results that are to be obtained and the kind of training that the interpreter has received, what kind and type of imagery is available, what are the instruments available, and what are the scale and other requirements of the final output map together with the accuracy. And as I said, external knowledge available and any other sensory surveys, any other surveys or any other kind of ancillary information that is available could also be used for better interpretation. Now the activities in a sequence that are applied are detection, recognition, analysis, deduction, classification, finally idealization, and then we converge all the evidence together and come to a conclusion as to what the object could be. Now once I am aware of the application for which the image is to be interpreted, it will dictate which kind of data I need to look at, which would be optimum or which would serve my purpose best and give me maximum amount of information. Not all kinds of data would be suitable for any kind of application. Say for example, if as a user I am supposed to make a regional level map of forest species, I would probably require more or better spectral resolution so that I am able to distinguish between different species of trees rather than having a fine or fine spatial resolution. So wherein I do not require great detail, but I require more spectral discriminability. Similarly, if it is a change detection study that I wish to do, I will look at temporally varying data. On the other hand, if it is an urban application which requires the user to have information at a higher level of detail, then maybe a spatial resolution of higher spatial resolution would be desired. Now the next important thing and the basis of image interpretation are the elements of interpretation, which help us in recognizing targets on the images and do information extraction process. So observing the differences between the targets and their background involves comparing different targets, and we do this based on either one or all of the elements or visual elements, which are tone, shape, size, pattern, texture, shadow and association. We will look at each of these one by one. Tone refers to the relative brightness or color of the object in the image. So if you look at this, wherever there is a change in tone, we see an edge. Now if I am able to identify all the regions where there is a abrupt change in tone, I will be able to identify theoretically all the object boundaries. Right? Now generally tone is the fundamental element for distinguishing between different features or targets. If I have a multispectral image, I can view the same object in color. Shape refers to the general form or structure or outline of the object, and certain objects have characteristic shapes, so we immediately connect the shape of the object to a particular kind of feature. So linear features, if I have linear shape, you could connect it to say canals or roads, sometimes rivers and so on. Right? Shape could be a very distinctive clue for interpretation. One should always remember that size of object on the image is a function of its scale or resolution. So the same object on the ground, if viewed at different spatial resolutions, will be seen in different sizes on the image. Right? The next element, which is pattern, this refers to the spatial arrangement of visibly distinguishable objects. This basically means that whether there is an orderly repetition of similar tones and textures in the image, or whether there is a haphazard sort of a pattern that is seen on the image. For example, orchards and forest areas. So, if I have an orchard and a forest, spectrally they will give me the same kind of reflectance, but if I look at the pattern, because orchards are planted in rows, trees are planted in rows, we will see that pattern because I have a vertical perspective of the area. I will see them as rows of trees and orchards with evenly spaced trees. Another example could be an urban area with regularly spaced houses. The next important element is texture, and this refers to the arrangement and frequency of tonal variation in particular areas of the image. Basically meaning that how soon does tone change in the image. So, if you look at this area, tone does not change very frequently and we see a single tone, and visually the texture appears to be smooth to the eyes. Whereas in the top half of the image, there are frequent changes in tone, bright, very bright, dark, and so on. So, you see a mottled or rough texture. You can easily mark out a boundary between the smooth and the rough textures. Okay. Texture is also one of the most important element for distinguishing features in microwave imagery. Shadows, though, are usually thought of as noise or occlusion. These may sometimes provide an idea of the profile and relative height of targets, which could make identification easier. When I show you certain images as examples, we will probably be able to understand better. They also sometimes give us a rough idea of the height of objects. Association, the feature of association or the element of association takes into account the relationship between other recognizable objects or features which are in proximity to the target of interest. So, there are certain features which always occur in association with certain other features. Say for example, commercial properties or commercial areas are characterized by their association and proximity to major transportation routes, whereas residential areas are associated with schools, playgrounds, sports fields, parking areas, etc. Now, if you look at this image, with the discussion that we have already had, we can use one or more of the elements of interpretation to make a distinction between certain features here. So, if you look at this feature, you could easily identify the racetrack using elements of tone, because there has to be a distinction between the object and the background. So, the tonal variations have to be there. Then the shape of the object is also distinguishable. Elliptical racetrack, river based on the spectral properties and the shape, roads, there are several roads that you can see here based again on the shape and the spectral variation, that is tone. Residential areas, again several areas here, and the dam is also associated with the river. So, even though the construction material of the road and the dam or the bridge may be the same, but we associate the bridge and the dam with the water body, and hence we are able to make a distinction. So, it is usually not just a single element which will help you as an interpreter to make a distinction between or recognize features. You will have to apply several of the elements together and come to a conclusion. Now, you could use single images or stereo images, multiple images meaning several images from different sensors, multi-band images multi-date images, temporally varying images, and multi-stage images. Multi-stage images would mean that you have images taken from a ground-based sensor or an air-based sensor and a space-based sensor. Now, interpretation of multispectral imagery basically depends on the resolutions, the stereoscopic ability. You could do it, the interpretation could be done individually on each band or multispectrally by combining the bands together, and you could use temporal data to do certain kind of analysis if required. One could have black and white panchromatic images, black and white infrared images, color infrared, or false color images. Okay. Now, if you look at this, we will now just go through a few examples of various kinds of images that are available. Now, this is a panchromatic film in the 0.3 micrometer to 0.9 micrometer range. So, the infrared band is included. So, water bodies appear dark in shade. Here you see this is a moving ship or a, so you see the texture here, and the roughness of the water body has been altered. Then on near the coast, the land water boundary, there are certain suspended material that are seen. As you go deeper with the increasing depth, the reflectance decreases. Here we have a comparison between the true color composite and a standard false color composite. So, you see features that are seen in green in the true color composite are seen as red features and correspond to vegetation. Built up areas are seen in their natural colors here, and they appear in the cyan tone here. Now, this is a middle infrared image taken in the mid infrared region of the spectrum. So, you see here it's a volcanic feature, volcanic crater with the burling lava seen in the orange yellow shade here. Vegetation is seen in the color red, and cyan tones at the base of the mountain are probably built up areas. Then this is a Landsat image of medium to coarse resolution. Here again you see a water body, cyan tones which correspond to either sand. There are small water bodies inland here and vegetation in the color red. Another scenario which is rather arid, dry area. So, you see the channel the river channel wherein we have water is dark, and where it becomes dry riverbed is very bright cyan tone. This is a list 3 image. If you see these circular features, these are usually found, these are agricultural fields, and these are usually found in dry arid regions, usually deserts. Now, because of the way in which the fields are irrigated, here because of a shortage of water, they use sprinkler irrigation systems. So, because the sprinkler operates in a circular fashion, so to make maximum utilization of water, the fields are also in a circular shape instead of the normal geometric square or rectangular fields that we are used to seeing. So, if you see here, red corresponds to vegetation, the dark areas correspond to moisture content, high moisture content. So, you see the irrigated part of the field is darker, the one that is not irrigated or has less moisture is brighter, some which are lying fallow, so no vegetation, so there is no shade of red here, and the cyan bright tone corresponds to the sand. Again the sea coast, so you see the beach, bright sand here, red is all vegetation, the water body, and suspended material near the coast. This is a delta region, a different sensor. So, you see here, because it is depositing silt here, lot of suspended material at the mouth of the delta, maybe because of moisture content, this half has a darker appearance and the other half has a brighter appearance. a very dry, arid, mountainous, rocky terrain again. So very few patches of red which correspond to probably small trees or vegetation areas. A city area. So this is a fused data product of LIS3 and PAN, and you see here this is an airstrip or an air. Here we see a stadium with covered seats and so on, several built up areas, roads, etc. Similarly here, agricultural fields in various stages of crop or fallow and various stages of growth. So dark red ones show crop at some maturity, some stage of maturity. Here the lighter ones are all fallow fields, and the ones which have pinkish tone are probably ones with young crop or grass, etc. This appears to be a water body, several pockets of urban areas, roads, etc. Now this is a spot image, multispectral image. Again we see the sea coast with the beach, waves in the water body, deep calm water which has a dark tone, and several vegetational features, built up areas and so on. Now here we see an image which is a 2-date image. The top one has been taken by a 1 meter resolution satellite, the Iconos satellite, and it's a true color composite, as you can see, on September 7th, 2001, and the bottom one is taken on September 12th, 2001. So if you see here and you compare it here, you are able to see the damaged portions of the building. So in the meanwhile there has been an incident which resulted in the damage of the portion here. So if you have two time or temporally varying images, we can use those to see what change has happened in the intervening period. Apart from that, we are also able to see certain other features like parking areas. Yes, it's an institutional building and so on. Vegetation features. Now if you look at this image, it's an agricultural scene, several agricultural fields in different stages. Some have crop, some are lying fallow, some have been freshly ploughed, so we are able to see, because of the high spatial resolution, we are able to see the furrows. Now in the tree area, orchard area also, you are able to probably make out different textures. These features that stand in the middle of the fields are windmills. So even though because of the vertical perspective we are not able to see the shape, but in some cases, some windmills, some features you are able to see. When you analyze the shadow, you are able to make out the shape of the fan. Maybe if you observe it later and download the material and see it, it will be much clearer. Now this is a 70 centimeter aerial image, and it depicts a nuclear facility. So it is an industrial area. You see chimneys, storage buildings, tanks, chemical tanks and so on. So associations help you analyze what kind of setting it might be. If you look at this and if you look at this, people who are familiar with desert areas will analyze that these are sand dunes, these are longitudinal sand dunes, and these are fan shaped sand dunes, right. So one can analyze, looking at these, one can analyze the direction of wind and how they must have moved and so on and so forth. This white bright feature corresponds to salt pans. Now I will show you how you may see the same kind of reflectance, but features are different because you see different associations. The feature that you see here is in the higher Himalayan mountain region, so, and it is white bright feature. These are glaciers, whereas the one that we just saw is associated with the sea coast and even though they have same reflectance pattern, they are both reflecting highly and are appearing as white features on the image. Similarly, if we see clouds, clouds would also appear similar in terms of spectral pattern, but again they have a different texture of cotton wool soft kind of texture, and they are associated with a shadow unlike the other two. Now here again if you see, it's a high resolution image, a chimney, the shadow is also very well visible. These are stacks of bricks and there are surrounding areas which have been excavated. So this is a brick kiln. Now if you are familiar with brick kilns and you are aware of the kind of excavations that happen, that you will have a chimney, you will have an oven and you will have stacked bricks. So you put all these elements together and might come to the conclusion that this could be a brick kiln. The spatial resolution is also high and it is displayed in the natural color composite or true color composite. So exactly the same colors as we see on the terrain in the actual objects. This is an urban scene, this is also an urban scene. So spectrally probably we will get the same kind of information on the image, but the pattern as you see, this does not have any pattern, haphazard sort of distinction, whereas here you see distinct streets with houses in rows and so on. Even here other urban features are visible. This appears to be a railway station, a stadium, roads, flyovers, and if you look carefully here in this area, this appears to be a bus depot because you see buses going in and vehicles coming out. You are also able to see some vehicles on the ground and so on. Right? Roads etc., built up areas, some industrial area here and so on. A very high spatial resolution image wherein you see several kinds of details. Even the markings on the roads are visible, the dividers are visible, each vehicle on the road can be counted. The entities on the rooftops like air conditioning units, water storage facilities etc. are also seen. So the details that this kind of imagery would be used for certain kind of applications which require high detail, greater detail to be interpreted. Again this is a high resolution image with an industrial setup. So storage buildings, storage sheds, tanks and so on. Right. Now this is just a comparison between manual and digital kinds of interpretation. Manual interpretation and analysis dates back to the early beginnings of remote sensing and it began with aerial photo interpretation. This kind of interpretation requires little if any specialized equipment. Manual interpretation is often limited to analyzing only a single channel of data or a single image at a time, usually, especially if I have a hard copy image. Manual image interpretation is also a subjective process, meaning that the results could vary with different interpreters. Comparing this with digital image processing, even though you have not been exposed to the technique yet, this kind of analysis is more recent, and with the advent of digital recording of remotely sensed data and the development of computers have influenced it. This requires specialized and often expensive equipment. The computer environment is more suited to handling complex images of several or many channels or from several dates. And this digital analysis based on the manipulation of digital numbers on the computer, and thus it is more objective. Not to say that it is always correct, but it generally has more consistent results because it is based on mathematical principles. On the other hand, this, as we say, is a subjective process. However, whenever we go about determining the validity and accuracy of the results from the digital process, it is very difficult because results are only what the user supplies to it. Reference image, the interpretation of human interpreters is still and always the best kind of interpretation and thought to be the most correct. So it is important to reiterate here that visual and digital analysis of remotely sensed imagery are not mutually exclusive processes. They have to be done together. In most cases, a mix of both methods is usually employed when you analyze images, and the ultimate decision of the utility and relevance of the information extracted at the end of the analysis process still must be made by humans. So reference for validation is always a human interpreted or a visually manually interpreted map or data. Right? With this we come to the conclusion and the end of today's lecture.